Martinez from Indiana University, and he's going to speak smallest scale estimates for the Navier-Stokes equation.
Okay. Thanks, Mimi. And also, thanks to the organizers for giving me this opportunity to speak here. I'm very happy to be here, especially be a part of this workshop yet again. So thanks. Okay, so I'll be talking about the smallest scales for the Navier-Stokes equations. And by smallest scales, I'm referring to the dissipation length scale for the Navier-Stokes equations. And the dissipation length scale is a length scale which indicates where the viscous effects dominate the nonlinear effects, or where they begin to dominate the nonlinear effects. So one expects, first of all, this length scale to be small. And for length scales smaller than this dissipation length scale, then the internal friction takes over and governs the flow from there. So one property in particular that happens in this within this length scale is that the energy spectrum decays exponentially for wave numbers larger than the inverse of this length scale. And by energy spectrum, I simply mean, so for example, the energy spectrum at wave number k, which is for amplitude of wave numbers k, it's simply going to be the sum of the square of the Fourier modes with time averages here. Okay. One picture to illustrate this is given by Kolmogorov's picture in 3D for his theory of turbulence. So on the y-axis here, we have the energy spectrum. And on the x-axis is just the amplitude of the wave number. And if we assume a low mode body force, then for these low modes, we'll see some non-universal structure. But then after that, there'll be a range of wave numbers where the nonlinear effects is what governs the flow. And this is called the inertial range. And Kolmogorov posits that the energy spectrum should obey a power law there of k to the minus 5/3. And then that inertial range extends all the way up to this dissipation range, which I've circled in red. And this is where the energy spectrum experiences an exponential cutoff due to the viscous energy consumption. And so the location of that dissipation range is what we're after, an estimate of where that's located. Okay. So another thing about in Kolmogorov's theory in 3D and in 2D for Kreisschnitt is how to obtain this dissipation length scale. So Kolmogorov posits that it should only depend on the dissipation and the viscosity alone. And so which dissipation in 3D, it should depend on the mean energy dissipation rate. So these brackets here you can think of just as long time averages. And the viscosity is nu. And if you construct a length scale out of that, then the one you get is given by this. So here I've written it as kappa epsilon as a wave number. So the length scale is just the inverse of that wave number. And in 2D, you do the same thing, except with the mean entropy dissipation rate, and you obtain this. So to estimate these things, you could, of course, estimate these quantities. But in fact, what we're going to do is estimate them through Javret norms. So which is more indirect, but I'll explain why we do that. And also, once we've done that, we'll compare those estimates to lambda epsilon and lambda eta. So for people checking the units on these things, I'm working in I might be missing some lengths here, but I normalized the length to 2 pi. So okay, so this is going to be the goal. All right, so here are the Navier-Stokes equations. We'll be working in the periodic case. As I said, we'll normalize the length of the periodic domain to 0, 2 pi. And of course, the initial data f are periodic, mean 0, etc., and U0 divergence free. Okay, so as I said, we'll be estimating the dissipation length scale through Javret norms. And the reason for that is because Javret norms characterize analyticity. So by Javret norms, one way to define them would be as follows, is to view it as a weighted little LP norm. So the weight here is just this exponential and this polynomial here. And the analytic Javert norm will be when this power in the exponential is 1. So when we just have k to the power 1 here. Then one can define the maximum radius of spatial analyticity by taking the supremum over the lambdas for which the Javert norm is finite. And of course, just by definition, you get the exponential decay of the Fourier modes when this norm is finite. And so this implies that the dissipation length scale is at least as large as the radius of analyticity. And so question would be is, does the reverse inequality hold? And if not, then how far away? So here's a short history of results. There are some missing, but the ones that will be relevant for this talk will be these that I've listed here. So in Foyash and Tamam in '89 introduced this Javert norm technique. And they obtain a bound on the radius of analyticity of Grashof to the -2 up to a log. And this Grashof number is just a measure of the force. So in fact, here we'll be taking the force to be finitely many modes and time independent. And again, missing some length scales here, but the length is normalized. So this is okay. In 3D, Doring and Titi refined this result of Foyash and Tamam, refined the analysis of Foyash and Tamam to obtain this estimate on the radius of analyticity. And so before I go on, let me say that this is joint work with Annemiek Biswas, my advisor, Mike Jolly, and also Idris as well. And they obtained this estimate in terms of the energy dissipation rate, but it's a supremum of the energy dissipation rate at time t here. And so they can couch their estimate in terms of the Kolmogorov length scale as lambda epsilon. I put a bar there because it's with supremum and not time averages to the 4th power. And to my understanding, this is the best estimate in 3D in terms of the Kolmogorov length scale. And then in 2D, the best known estimate is by Igor, and he obtained that the radius of analyticity is bounded below by Grashof to the -1/2 up to a log. And in a certain turbulent context, you can actually couch this in terms of the dissipation length scale in 2D, the Kreischian length scale, and actually it turns out to be lambda squared. So where our results fit in here is the following. So they're rather modest, as you can see. There's no improvement on the exponent, but in the 3D case, we've removed the bar. So we've been able to couch the estimate of the radius of analyticity in terms of the actual Kolmogorov length scale. That's one thing. And for the 2D case, we essentially recover the Kukovica estimate of lambda A bounded below by the Kreischian length scale squared. And this P here is because we have these holding with large probability P with respect to some time average measure, which I'll explain briefly later. And our analysis shows actually that in 3D, it seems that one can push it down to 7/3 perhaps. There's hope for that. Okay. Yes, with the P still there. Yes, thank you. Okay, so although the results seem incremental, there are still a few nice observations that we can make. First of all, we obtained these results by working with Javert norms, and on top of that, by working in the Wiener algebra, so with little L1 norms, which of course has the structure of an algebra and turns out to be well suited for working with Javert norms. And this was actually crucial to obtaining our 2D estimate. And of course, this is consistent then with the story painted by these results, Oliver and Titi, and Gerard, Yanchu, and Idris, to some dispersive equations where they obtained essentially sharp estimates on the radius of analyticity there. Also, we improved the Charlie and Idris's result by replacing the lambda bar by an actual Kolmogorov length scale in terms of time averages. So this is in a particular turbulent context, which I'll explain later. And we also are able to just put in any type of forcing, analytic, of course, but arbitrarily many modes. And of course, so the Kukovica result, so Igor used, he extended the Navier-Stokes equations, he complexified the Navier-Stokes equations and estimated in LP the approximate solutions of this complexified system. There were some delicate estimates made there in order to obtain a good existence time. So it's rather comforting to know that in some suitable sense we can recover that estimate using this Givray norm technique. So for the rest of the talk, I will explain where the more general theorem from which these estimates follow, and also this turbulent context where they hold. Okay, so here's just some notation, just the bare minimum to get to the theorem. We'll denote the Wiener algebra by W. MF will denote the size of the forcing, and Q will be the time integrability of the force. This is just the Givray norm, but in the Wiener algebra. So, and P is the Leray projection onto divergence-free vector fields. So here's a fact. This quantity M, which I have to represent the size of the force, is actually comparable to the Grashof number when the forcing is time independent and has finitely many modes. So you can think of it for the rest of the talk as just being the Grashof number. And the theorem we have is the following. So sigma, if you take sigma between -1 and 0, then if the initial data satisfies this estimate, this A here, which I should have said earlier, is the Stokes operator. So you could think of it as just the Laplacian since we're working in the periodic case. And if it satisfies this upper bound estimate, then the radius of analyticity, there's a mild solution that exists whose maximal radius of spatial analyticity at time t star is bounded below by this. So when Grashof number is large, we pick up this estimate. And in the special case of the Wiener algebra, this is what the theorem specializes to. So notice here we don't have the endpoint case of sigma equals -1, but this was already done by Ley and Lin, and then later by Biswas in 2012. But I won't talk about that. And it actually doesn't give any improvement to the estimates to have the sigma equals -1 case. Okay, so you see here in 2D, this is already the Igor's estimate. And so we just need to verify this hypothesis. And this is where we specialize to the context of turbulence. So in 2D, what do we define to be a turbulent flow? We'll say that the Grashof number is large. So this is, it's known if the Grashof number is too small, then there is no turbulence. So we assume Grashof number is large. This second one simply says that the bulk of the energy is located in the inertial range. So the P is just a projection onto the modes up to kappa sub I, and Q is the complementary projection, so the tail. And this kappa sub I bar will be the left endpoint of the inertial range, and kappa sub I upper bar will be the upper range. And so you see this third assumption is just going to be another version of the Kolmogorov power law, and we're just stipulating that it should hold over the inertial range. Okay, and then Daskaluk, Foyash, and Jolly in a paper in 2008 show that these estimates hold in this context on the energy dissipation rate and the entropy dissipation rate. And here again, you can think of these as long time averages. But actually, let me say a little bit more about that now. So these long time averages, I'm saying that's with respect to a time average measure on mu. And so the way we're getting this is by using this generalized Banach limit. So You see, by using this generalized Banach limit, we don't have to say anything about ergodicity or anything like that. So we have that this generalized Banach limit is given by this measure, and we call that measure time average measure. Okay. So that's what those brackets, this is a definition for the bracket. All right. So using these estimates, so first of all, we apply Brézis-Galloway. So we use the time average version of it. And then using the estimates from the Daskaluk-Foyas-Joly paper, we are able to verify the hypothesis of our theorem. And so now using the Chebyshev inequality, we can obtain that actually this is verified on, that this hypothesis is verified on a large portion of the global attractor. So that's where the turbulence come in. It's to verify the hypothesis of our theorem. And the story is similar in 3D as well. So this would be the formal statement of the result in 2D. So the story is the same in 3D, or similar in 3D. In fact, the way we define turbulence is slightly. We don't need that second assumption where the bulk of the energy is in the inertial range, and performing the same kind of argument, we obtained the estimate that I had said before of the radius of analyticity being bounded below by the Kolmogorov length scale to the power 4. So let me just say a brief word about where we think 7/3 comes in. And so recall that in 2D, we used the improved estimates on the energy dissipation rate and the entropy dissipation rate to obtain to recover the Kukovica estimate. But in 3D, we don't have an estimate on the energy dissipation, on the entropy dissipation rate. But if we have something on this alpha to the 3/4, if we have some estimate on alpha to the 3/4 of u, for example, Grashof to the 7/4, which naively could be this, then we get the 7/3. And in fact, if we get anything less than 2 here, we would get something close to 7/3. So basically, the conclusion is, estimating this quantity. What does it come out to be? So let me just say one more thing. Let me just conclude, actually. So the 2D Kreisnin theory actually indicates that that the Kreisnin length scale should actually be Grashof to the -1/3. So the radius of analyticity estimate given by Igor is Grashof to the -1/2, and rigorous estimates give this bound on lambda eta, not through the radius of analyticity, just estimating lambda eta as it's defined directly in this Foyas-Manley-Tamam paper. And so the question is, this is still an open problem. How far can we get closer? Can we break the Grashof to the -1/2 bound, possibly under some turbulence assumptions? And actually, our theory indicates that there's some evidence for this as long as we have the proper bounds on the initial data. So let me stop there.